Hello and welcome to Deeksha Karnataka YouTube channel, and in the PU1 series today I am going to discuss three chapters of heat, thermal properties, thermodynamics and kinetic theory of gases. So these three chapters are important chapters. Each chapter generally consists of one question, is not two questions. Previously from thermodynamics we used to get two questions. Now it is only one question. For last 5-6 years we are getting one question each. Generally questions are relatively easy, not that difficult. So if you go through this lecture you should be able to answer the three questions. So let us look into the chapter highlights. In the thermal properties we are going to discuss ideal gas equation, specific heat, heat transfer and black body radiation, including Newton's law of cooling, which is very important. In the thermodynamics chapter we are going to discuss laws of thermodynamics, first law, second law. We will also discuss specific heat capacity, thermodynamic processes and Carnot engine. Everything will be discussed. Now some students may have a confusion that Carnot engine is deleted. Carnot engine is not deleted, refrigerator is deleted. Carnot engine is still part of the syllabus. In the kinetic theory of gases chapter we are going to discuss pressure of an ideal gas, equipartition of energy, ratio of specific heat, which is very important, and mean free path. Okay, so this is all the three chapters that we have to discuss today. So three chapters in a single lecture. So let us start. Now let us continue with the next chapter, thermal properties. So in the thermal properties we have ideal gas equation. What is ideal gas equation? We all know one of our old familiar formula, PV equals to nRT. P is pressure, V is volume, N is number of moles. Some of your textbook do write this as mu nRT. Okay, so both are same, mu RT or nRT. Okay, so whatever formula that you have studied, that is the same, but only thing that mu and n are number of mole. So if you know the formula, it does not matter whether you are writing mu RT or nRT, because in the exam they will not ask you this formula, but maybe they will ask you a problem based on this formula. Okay, and one more important part is that P1 V1 by T1 is constant, and that is P1 V1 by T1 equals to P2 V2 by T2 equals to P3 V3 by T3. So basically this is a constant quantity. This is the ideal gas equation. Now ideal gas equation, there are some postulates of ideal gas, that all the gas molecules are rigid and they collide elastically with each other and they occupy no space, etc. But based on that there was no question on concepts of postulates, so that's why I am not discussing that. Now in thermal expansion, what is thermal expansion? Thermal expansion is you have an object, and if you apply some heat onto it, the object expands. Okay, so that is called thermal expansion. Now in this chapter mainly we will discuss about expansion of gases. Okay, and coefficient of volume expansion. Now in case of gas, what happens is that you can increase the volume or you can increase the pressure as well. Okay, because for normal solid and liquid, if you apply heat, only its volume increases. Okay, pressure atmospheric pressure is constant, so that's why the pressure does not change, but the volume increases. In case of gases, because they have no shape, what you can do, you can keep it under a fixed container having the pressure fixed. Okay, and you can increase its volume, or you can keep its volume fixed and increase the pressure. Okay, both way it is possible. So that's why it is very important that you mention which quantity you are describing. So volume coefficient or volume expansion coefficient alpha V is given by dV by V, that is change in volume, into 1 by dt. Okay, and 1 by V dV by dt. And for ideal gas, this volume expansion coefficient is 1 by T. There was a derivation in your PU1. Those who have done it remembers it. Those who don't, just remember volume is 1 by T. Volume expansion coefficient is 1 upon T. Okay. Now what about pressure coefficient? Pressure coefficient similarly can be written as change in pressure divided by original pressure into change in divided by change in temperature. Okay, so how you change the temperature, based on which how the pressure changes. Now this has no fixed value. Based on problem to problem you might require to solve it, but based on this there was no question in previous year papers. Now specific heat, let us discuss about specific heat. Is important concept. Based on this, obviously we have seen many questions in last 10 years. So specific heat is the change in temperature of a substance when given quantity of heat is absorbed or rejected by it. Okay, so you apply some heat, okay, and application of heat does not necessarily mean that its temperature will increase uniformly. Different materials increases their temperature differently. For example, if you give a very high amount of heat to water, its temperature increases very small, okay, because the specific heat of water is very high. Similarly, if you apply the same amount of heat to iron, okay, the increase in temperature for iron is much higher. Why? Because specific heat of iron is much smaller. So same amount of heat is a quantity, okay, temperature is a measurement. Okay, generally you cannot directly measure heat. There are other ways to measure heat, but anyway, unit of heat is calorie, and unit of sometimes it is also in SI unit is joules as well. Unit of temperature is Celsius, Kelvin, Fahrenheit, etc. So when you apply some heat, when the heat is being absorbed by the object, its temperature increases. Now based on its specific heat, okay, higher the specific heat, it can absorb more amount of heat. Okay, now what is latent heat? Latent heat is the heat required during the change of state, depends upon the heat of transformation and mass of the substance undergoing the change of state. Okay, so for example, you want to melt ice from you want to melt ice into water. Okay, so you have to apply 80 calorie per gram heat. Okay, so that is called latent heat per gram. This is a fixed quantity for each object and concerning state. Okay, so if you are concerned, for example, if you want to boil water from water to steam, okay, you have to supply 540 calorie per gram amount of heat. Okay, so heat changes based on which state you are changing and which object you are changing. Generally the values will be provided to you. Okay, if there is a problem based on this, either they will mention the S or delta T or M or L, those values will be provided to you. Don't worry, just remember that latent heat is the state where the heat which is required to melt or boil something. It can be water most commonly, or it can be any other substance as well. Now calorimetry, very important concept of calorimetry. Calorimetry says that if there is no heat loss, okay, the heat loss by one object is heat gain by another object. If there is no heat loss into the atmosphere, there are ways to do it. Generally not any equipment is 100% perfect, so some heat actually releases into atmosphere, but in controlled environment that is possible. So if you have suppose two objects in contact, so objects A and object B, both objects are in contact. Now the temperature of, say, this one is T1, temperature of this is T2. Suppose T1 is greater than T2, so this one is hotter temperature wise, this object has higher temperature than this another object. So what will happen, this object will give away heat to the second object till they reach an equilibrium temperature. Okay, they will reach, both of them will reach an equilibrium temperature T, which is not average of T1 and T2. You have to calculate that. How to calculate? There are ways to calculate it. We will explain in if not in this video, we will explain through our PYQ session anyway. But remember that when the heat is being exchanged, the heat loss, this object is losing heat. Okay, this object is losing heat, this object is gaining heat. So whatever amount of heat is lost by one object, the same amount of heat is gained by the other object. Okay, that is conservation of energy. Okay, so calorimetric principle is based on conservation of energy. Heat lost by one object is heat gained by another object. Now obviously, as I mentioned, it is specifically done in a controlled environment, because this object being in contact with surrounding, being in contact with the atmosphere, which is generally in lower temperature, it will radiate some heat to atmosphere as well, but we ignore that part. Okay, now few formulas to remember. Conduction, okay, this formula is important. So heat conduction per unit time, that is you can say that dq by dt. How much heat? Suppose we have a rod, okay, one end of the rod is say at a temperature T0, another end of the rod is T. Okay, so how much heat is being transferred from the hot? Suppose this is the source, okay, this is where you are heating it, and this is where you are measuring the temperature. So how much heat is being transferred, the rate of transfer of heat is given by this formula. Okay, so let me use the notation given over here. Okay, so here we have given this one is TD, this one is TC. So the heat that is being transferred from C to D, okay, given by this formula. Okay, so C is hot, obviously D is small. So this is the rate of heat transfer. Rate of heat transfer means the heat that is being transferred per unit second. Okay, per unit second, that is the rate of heat transfer. Here you have to remember that the rate of heat transfer is actually, if you see in the equation, proportional to the area, and it is proportional to 1 upon the distance. So suppose this is the length, so it is 1 upon length. Okay, so it is inversely proportional to length. Longer the distance, slower the heat will travel. Higher the surface area, more quickly the heat will travel. Now sometimes in exam they will ask the radius is given. Okay, the radius given means, or diameter is given, that means it is basically pi r square or pi d square by 2. So dq by dt is actually proportional to r square upon L. Okay, remember this will be very helpful. Okay, so rate of change is actually proportional to r square by L or d square by L, because even though r is d by 2, if you do the proportionality, the constant goes away, so it is d square by 2 as well. So if you see a question based on this concept where the diameter is being asked, don't worry, it is d square by L. Now what about other laws? Black body radiation. Black body radiation is when an object is radiating heat, assuming the surrounding temperature is 0 Kelvin, a hot black body. Black body means what? Black body means a perfect radiator. Okay, any object which is 100% black, okay, it radiates entire amount of heat, or it absorbs complete amount of heat. Okay, so absorption and radiation is absolute, then though that object is called black body. It's an ideal object. There are some ways to design perfect black body, but anyway we are not going into that concept. So for black body, the heat radiated is proportional to temperature to the power 4. Okay, it is proportional to temperature to the power 4. Actually it is proportional to temperature to the power 4 minus surrounding temperature to the power 4, but we assume that surrounding temperature is very cold. It is not relevant over here, so it is basically proportional to temperature to the power 4 of the hot object. Now here remember that this temperature has to be taken in Kelvin. In this chapter, whatever temperature that you consider, most of the cases except calorimetry and except in Newton's law of cooling, generally all the temperatures taken, for example ideal gas equation, okay, Stefan-Boltzmann's law, those are temperatures are always taken in Kelvin. This temperature you can take Kelvin as well as in degree centigrade, does not matter, because this is a difference. In case of difference cases, you can take degree Celsius or in Kelvin, does not matter. In case of calorimetry, generally the units are given per degree Celsius, so you have to take it in degree Celsius only. Newton's law of cooling, again it's a difference temperature, that's why you can take in Kelvin or degree Celsius, but most of the question comes in degree Celsius, so we will be taking degree Celsius only. Okay, so Newton's law of cooling, that how quickly an object can cool, it depends on two things: the temperature of the object and the surrounding temperature. Okay, so basically the difference in temperature minus temperature of surrounding is basically how quickly an object cools. Here d theta is difference in temperature from where to where you want to cool it. Okay, we will see it through a problem, don't worry. And if you solve this equation, you get T2. T2 is the final temperature, equals to T1 plus C into e to the power of KT. K is called Newton's law cooling constant. Okay, the same K here. So you can see that the temperature cools down exponentially. Okay, so even though it's not a direct exponential function, there is an addition over here, but you can say that eventually the object which cools down exponentially with time. So this is the temperature of the object cools down exponentially. Now let's move on to solve one question. A pan filled with hot food cools from 90 degrees Celsius to 86 degrees Celsius in 2 minutes when the room temperature is 20 degrees Celsius. How long it will cool from 74 to 66 degrees Celsius? Now very interesting question. So pan filled with hot food cools from 94 to 86. So it cools from 94 to 86 in 2 minutes. So basically d theta by dt. So I told you d theta is the difference in temperature when we calculate from where to where it cools down. But this is not the room temperature. Remember, this is not the room temperature. So 94 is the initial temperature and 86 is the final temperature, and we will use it in degree Celsius only. No need to convert any units in this kind of problems. Time is given 2 minutes. Again, we are not converting it into seconds, we are keeping it into 2 minutes. Okay, because our final answer will also be in minutes. So you can check that in the option as well. So 94 minus 86 is 8 by 2, which is equal to 4. And its unit is coulomb per minute, but degree Celsius per minute. You can keep that aside. So the how the rate of change of temperature happens is basically this. Now according to Newton's law of cooling, d theta by dt is T minus T surrounding into the Coulomb's constant. Okay, so this is the case number 1. Now very important thing, how to take this T. Once you understand this, your life is sorted. And Newton's law of cooling is one of the favorite topic among the teachers. It was coming almost every alternate year, but nowadays it is not coming too often. So maybe this year you will get a question based on this concept. So be prepared. Okay, so what is this T? The T is actually, here is mean temperature between from where to where it cools down, because it is not very simple, because it depends on the surrounding temperature. So here this T you have to take not 94, not 86, but the mean temperature from where to where it is cooling down. So during this time, what is the average temperature? Okay, so average temperature is 90 degree. Okay, 94 minus 86 is 170, sorry, my mistake, it is not 90 degree. Let's see, no, it is 180 by 2, it's 90 degrees, yes, I was correct. So 90 degrees Celsius is the average mean temperature. Now we will go back to this equation and we will use it, but before going into that, I will teach you a neat trick that you can use. Okay, because otherwise you have to calculate K, put that value of the K. I will show you a method where you don't need to use the value of K. Okay, so for that we have to go to the second case. What is the second case? It is cooling down from 74 to 66. We need to find the corresponding time for that. So d theta, or change in temperature, is 74 minus 66. Again it is 8 degrees Celsius. Okay, what is dt? We do not know. So d theta by dt is, say, because time taken, say, is t minutes, then it will be divided by t. So 8 divided by t. So d theta by dt is, so they will give you intervals such that both intervals have the same temperature difference. So you might think that okay, 8 degree there it will take 2 minutes, so 8 degree here also it will take 2 minutes. No, it depends on from where to where it cools down. Again we have to calculate the mean temperature. Okay, T mean, say this is T dash, and that is given by 74 plus 66 by 2, which is equals to 70 degrees Celsius. Okay, so now we will use this formula again. So first case, d theta by dt is 1, so this is say d theta by dt 2. Now once you have solved this kind of questions 2-3 times, you don't need to write everything, you can just write once and you can solve it. Okay, now let us do that. So because I don't want to disappoint you by skipping steps, so that's why I'm writing this. Everything later on you will say, sir, I did not understand, please explain me once more. So this is how it is done. So T minus Ts into K and T dash minus Ts into K. So K cancels. K cancels. What is d theta by dt 1? D theta by dt 1 is 4. So we know this value 4. So this will be 4 divided by, what is d theta by dt 2? D theta by dt 2 is 8 by t. We do not know the t, so it will be 8 by t. What about on this side? This side, what is t? T is 90 degrees. And what is Ts? Ts is T surrounding temperature. Surrounding temperature is given here 20 degrees Celsius. So don't worry, everything is given. 90 minus 20. What about T dash? T dash we have calculated 70 degree. And what is surrounding? Surrounding temperature remains same. Okay, now let's simplify. It will be 70 divided by 50. 0 cancels, so it is 7 by 5. Don't worry, we will come back to that. Now let us simplify this side. This t was in division of division, so this will go up. So 4t by 8, so it cancels, we get 2 over here, that is 7 by 5, or t equals to 7 into 2 by 5, that is 14 by 5. And if there is a division by 5, what you have to do? You need to multiply this number by 2 and then put a decimal. Okay? If any number divided by 5, what you can do? 2x by 10. Right? So this is the trick to remember. Whenever you see a division by 5, always double the number and then put a decimal in between. Okay, first one decimal. Okay, if suppose the number is say 90, then it will be 180 by 5, 180, then it will be decimal, so it will be 18, right? Even though 90 by 5 is divisible, but suppose you have a number say 66, how to do that? So in that case, double the number 132 and divided by 10, that is 13.2. So whenever you see a number divided by 5, always double the number, then put a decimal. Okay, so correct answer is 2.8 minutes. Okay, we will solve this question again in PYQs. So if you have doubts, don't worry, this is a PYQ. We will be solving again similar question. Now let's move on to the next chapter, thermodynamics, last chapter of the day. So thermodynamics is basically where we are dealing with systems. System means it can be anything, any object, an engine, okay, a refrigerator, they are all considered to be systems. So first we are starting with the zeroth law. Now there is a history of zeroth law. Most of you know that. Why it is called zeroth law? Because first law and second law was already given by people who exist there. Okay, Kelvin and all team, they already well established the laws of thermodynamics. First law of thermodynamics, second law of thermodynamics, they are all established. But suddenly after some time, Pauli, there is a person called Pauli, he discovered that there is one more law, and that law is more fundamental than first law and second law. That's why, because first law and second law is already occupied, and already many books are published based on first law and second law. So if you want to change the laws, you have to republish everything, and that will be very huge monetary problem. So they decided, okay, let's forget it, let's name it zeroth law. Okay, so that is zeroth law, and that's how the zeroth law came into picture. So what is zeroth law? Zeroth law is very simple. It says that two systems in thermal equilibrium with the third system separately are in thermal equilibrium with each other. So if suppose this is the diagram, okay, suppose this object A is in thermal equilibrium with object C. What is the meaning of thermal equilibrium? The meaning of thermal equilibrium is the heat exchange is zero. That means the temperature of this object, actually from zeroth law we get the concept of temperature. Okay, so the temperature of this object is same as temperature of this object, because if there is a temperature difference then only heat exchange happens, but if there is no heat exchange, that means this object is in these two objects are in same temperature. Okay, now that means what? That there is no heat exchange between A and C. Similarly, there is no heat exchange between C and B as well. Okay, so if there is no heat exchange between A and C and B and C, now if you add these two together, then the heat exchange between A and B will also be zero. Okay, the heat exchange between A and B will also be zero. That is the zeroth law. So heat exchange between A and C is zero, B and C is zero, then heat exchange between A and B will also be zero. So this experiment was done such a way that here initially this is a conducting surface, so heat can exchange between A and B and C, but once the thermal equilibrium, but there is no heat exchange between A and B. Okay, they are insulated. This surface was initially insulated. Now once the heat exchange is over, when the thermal equilibrium is reached, now they replace this insulating medium with a conducting medium, and they observe that no heat is being exchanged between these two objects. That is how the experiment was done. Anyway, this is a theoretical concept, no mathematics here. So if you see a theoretical concept based on this, you will be able to answer. Now let's move on. First law of thermodynamics. After zero is first. So what is first law? First law is basically conservation of energy. First law talks about conservation of energy. The energy supplied to a system. Okay, the energy that you supply, or heat energy basically here, because we are talking about thermal physics, the heat energy that is supplied to the system goes in partly to increase the internal energy of the system and rest in the work on the environment. Okay, so for example, suppose you give 10 joules of energy to a gas. Okay, 10 joules of energy to a gas. What the gas will do? Gas will keep 2 joules of energy in its pocket, and remaining 8 joules will go into doing some work. Okay, it can be increasing its temperature, it can be lifting something up, or whatever it is. For example, I can give you a real life example which is very bad. Suppose there is a corrupt official, and the corrupt official gets a grant of doing some road work, road repair work. Okay, the corrupt official, what he did, he got a grant of 1 crore. Okay, 1 CR he got to repair a road. What he did, he put 20 lakhs in his pocket. Okay, that is his internal energy increase, and then remaining 80 lakhs he gave it to the contractor to repair the road. Contractor did the assuming contractor is ideal, he did the road repair work. Okay, so gases also work in the same principle, the way our system in India works. This is very unfortunate, but anyway, this is just an example. Don't put me on anywhere if you see this lecture, obviously, but this is just an example. Okay, so remember that whenever you give some energy to the gas, what happens? The gas keeps a part of it in his pocket, and what does that do? So that basically increase the kinetic energy of the gas system. Okay, so the internal energy basically means the kinetic energy of the gases. Okay, the gas keeps a part of its energy, and that basically increases its temperature, and remaining it does work. So what is the meaning of doing work? Meaning of doing work means it basically generally increase in its volume. Okay, so the volume increases because of the heat that you provided. So in terms of gas, the work done always represents work equals to P into delta V. Okay, P can be constant, P can be variable, does not matter. As long as you see a change in volume, the gas has done some work. If the volume is not changing, then the work done by the gas is zero. That means entire energy that you supplied is actually converted into internal energy. Okay, so when you supply a heat to a system, the system absorbs some of the heat for its own internal energy, remaining heat, it goes into the work done. Okay, work done is always P into delta V. In integration terms, it is P into dV. Okay, so if they give you that the P is given, what is the work done, you just need to integrate it. Okay, now area under the PV graph represents the work done by the gas. Generally, what question you will get in the exam is based on this. Suppose this is P, this is V, okay, and this kind of graph will be given to you. You will be asked what is the work done. So work done in the PV graph is basically area under the graph, this area. Okay, so this area you have to calculate. How to calculate? You check what is the initial P, what is the final P, so delta P here, and what is the final V, initial V, what is the final V, then delta V over here. So the area under the graph is basically half delta P delta V. Okay, so this is the area under the graph. This is a triangle. Mostly triangle will come or rectangle might come, but no matter what shape they give you, you only need to remember one thing, that area under the graph represents the work done. Okay, first law is the direct consequence of the conservation of energy. I already mentioned that. Now let's move on to a question. Okay, exactly same question that I was talking about. 1 mole of an ideal monoatomic gas is taken round the cyclic process MNOM, the work done by the gases. So here the gas undergoes a cyclic process M to N, N to O, and O to M. Then what is the work done? How to calculate that? So the very easy thing, you need to calculate the area under this graph. Okay, so how to calculate? Initially pressure was P naught, final pressure is 3 P naught. So what is the change in pressure? Change in pressure is 3 P naught minus P naught, that is 2 P naught. What is change in volume? Initial volume is V naught, final volume is 3 V naught. So change in volume will also be 2 V naught. Okay, this is delta V, this is delta P. Okay, now what is the work done? It's very simple. Work done is given by half delta P delta V, that is area under the graph, right? So half into 2 P naught into 2 V naught, one of the two is cancelled, so it will be 2 P naught V naught. Okay, it will be 2 P naught V naught. Option D is correct answer. Okay, now let's move on. Specific heat capacity. So specific heat capacity is something similar to the specific heat. Okay, specific heat is we generally discuss for solids, but specific heat capacity is more important for gases. Now what is specific heat? Specific heat is the heat you give and the temperature increases. So what is specific heat capacity? Specific heat capacity is how much heat you supplied and correspondingly how much temperature increases. The ratio of that is called specific heat. Okay, we will discuss more about this in our next chapter, kinetic theory, don't worry. So what is Cp and Cv? For gases, okay, you can increase its temperature by keeping its pressure constant or by keeping its volume constant. Okay, you can keep the volume constant, you giving some heat into it, and the gas increases in pressure and temperature. Okay, so basically Cp means constant pressure. So the heat you supplied, that corresponding increase in temperature divided, and it represents P is constant. Okay, many of you have trouble to understand what is the meaning of Cp, Cv. Okay, so whenever something suffix is written, that means that quantity is constant. Okay, and what is Cv? Cv is delta Q by delta T, where volume is constant. Okay, generally Cp, always Cp is greater than Cv, and Cp minus Cv equals to Nr. For 1 mole of gas, it is equals to R. okay, and gamma is called the ratio of specific heat capacities. There are few more formulas based on this. We will again discuss that, as I mentioned, in the next chapter. Now, thermodynamic process. Let us understand few thermodynamic process. Maybe I will repeat this again in the next chapter, don't worry. Okay, thermodynamic process. What is thermodynamic process? Thermodynamic process is basically based on how the heat is being transferred or how you are treating a system. You can do a lot of things with gases. That's why gas can be little bit complicated. What things you can do? First of all, isothermal process. What is the meaning of isothermal process? Isothermal process means you are keeping the temperature of the gas constant. Okay, you are keeping the temperature of the gas constant. In that case, what happens? The P into V, the multiplication of P into V will be constant. And if you draw a graph of PV, in case of isothermal graph, it will be a rectangular hyperbola only in the positive quadrant, first quadrant. The other quadrant, obviously it is not there. Gases pressure cannot be negative, volume cannot be negative, so that's why it is only in the first quadrant. You know the hyperbola, right? This is the hyperbola. So this quadrant, fourth quadrant, third quadrant is not there because pressure and volume are always positive. Okay, so this is the representation of PV diagram. This is called PV diagram. Okay, PV diagram can be anything, but for isothermal process the graph looks like this. For any other process it may not look like this, but for isothermal process generally the graph looks like this. Okay, now there are few other processes. Isobaric process. Isobaric process means pressure itself is constant. Okay, so here only P is constant. Okay, what about isochoric process? Isochoric process means volume is constant. Okay, based on this maybe you might see a small conceptual question, so you have to remember this term bar. Remember that bar means pressure. Okay, bar is a term which is used for pressure. Core means volume. Okay, core means volume. So isobaric means same volume. Iso means constant. Iso means constant. Isothermal, thermal means temperature. Okay, thermal represents temperature, so isothermal means constant temperature. Isobar means constant volume. Isobar means constant pressure. Isochoric means constant volume. Now apart from this, there is one more process which is adiabatic process. Adiabatic process is exactly opposite to that of isothermal process. Here no heat is exchanged. So you basically what you do, you have a gas. Okay, you are not allowed any external heat, but you just change the pressure or change the volume of the system by applying external force. Okay, suppose suddenly you allowed a gas to expand. Okay, suppose you have a chamber like this. In this chamber you have some gas. Okay, there is a partition over here and the other chamber is vacuum. Suddenly you remove this partition, then all the gas will expand over here. Okay, what will happen to the volume? Volume increases, obviously, where gas takes the volume of the container, so its volume increases. What happens to the pressure? Pressure decreases. What happens to the temperature? Temperature will also decrease. Now this is an adiabatic process, a sudden process. Adiabatic is a sudden process, and in this case you are not applying any external heat. The system undergoes the changes on its own. That is called adiabatic process, and in adiabatic process delta Q is 0. So from first law of thermodynamics, whatever delta Q is 0, so whatever work gas is doing is basically from its internal energy. Whatever work the gas is doing is from its internal energy. So it is minus du. Okay, dq is equal to w plus du. So basically the work done will be in the expense of its internal energy. And in adiabatic process, Pv to the power gamma is constant. Pv to the power gamma is constant. Okay, slope of adiabatic graph is more than the isothermal graph. So if you see a graph like this, so mostly this is isothermal and this is adiabatic. Okay, because if you calculate the slope of this graph is more steeper. Steeper means it starts with a higher value and suddenly it falls to 0. Okay, it falls much quicker compared to isothermal process. Isothermal process is more regular graph. Okay, it's a more regular kind of a graph. Adiabatic graph is also a hyperbolic graph, but in this case it falls steeper. Okay, the slope is actually gamma times more than that of isothermal graph. Okay, so the slope of adiabatic graph is gamma times more than isothermal graph. Okay, remember this. So slope of adiabatic graph is more than isothermal. So what is slope, by the way? How to calculate slope? You need to draw a tangent, you need to take the y, you need to take the x. Similarly for adiabatic also, you need to draw a tangent, you need to take the y, you need to take the x, but for adiabatic graph, for same x, the y value is more, slope is more. Slope is same, that concept that we have learned, right, in mathematics, in laws of motion chapter, same thing applied to this graph. Okay. Now second law of thermodynamics used to be very long and complicated. Now the concept is simple now. Only Kelvin-Planck statement is there. Kelvin-Planck statement is no process is possible whose sole result is the absorption of heat from a reservoir and complete conversion of the heat into work. Suppose you have a reservoir. Reservoir means heat reservoir. Okay, basically like a gas oven, okay, which is always hot. Okay, pizza oven, or a normal tandoor, which is always hot. There are coal inside. So suppose you have a source, okay, and you are taking, this is your device means which works on this heat. For example, pizza, you are baking a pizza. Okay, so that can be considered to be your system. Okay, this is your system. Generally we say this is an engine. Okay, it can be anything. Okay, this is your system. Okay, no process is possible whose sole result is the absorption of heat. So it is absorbing the heat from the source and it is doing some work. So what is the meaning of that? The pizza is absorbing the heat and it is converting into from a dough to pizza. That is the process. Okay, but it says that it is impossible to do that. So what it will do, it will actually emit whenever it is taking some heat. Suppose it is taking some heat, say Q1, and it will release some heat to something called sink. Okay, so when the pizza is getting hot, it is not only absorbing heat, it is also releasing heat at the same time. When it is absorbing heat, it is also releasing heat. Now whom it is releasing heat? The surrounding. Okay, surrounding is always colder, so it is always emitting heat when it is absorbing heat. Okay, so this is how any thermodynamic system works. Thermodynamic system example is not pizza but the engine. Okay, the engine of your car, engine of your bike, okay, or engine of your school bus. So they all work in this principle. So, and how the heat is being generated when the petrol is burned inside your engine, heat is generated, and who is the sink there? Obviously our own very old good friend environment, which is a colder temperature. Being in colder temperature, that helps to radiate the heat and our engines work. If you take the same engine maybe in say Jupiter, it will not work. Jupiter is much hotter than Earth, so whatever is your working temperature in Jupiter, that might not work. Okay, it will work in Mars, but it will not work in Jupiter, being a hot planet. Okay, so surrounding temperature has to be colder than the engine temperature, so that the engine can radiate heat and work. Okay, so what is the work done then? Work done is basically the difference in the heat. So this much work the gas or the system will do. Okay, so remember that actually first law prohibits that whatever heat you are taking, the entire heat will be converted into work. Some part of the heat you have to release back to the sink so that you can work properly, you can function properly. That is Kelvin-Planck statement. There is a Clausius statement which I don't think is important, so I am not keeping it. Anyway, there is nothing, no application related to Clausius statement is there, only the statement is there. Okay, so remember that no heat, you cannot only absorb heat and convert the entire thing into your work. So whatever you are studying, You cannot remember everything. That is, next time when someone says that if you can't remember this thing, you just tell them that whatever I study, I cannot remember everything. I have to give something back to the environment. But what is the environment for you? It is the notebook. So if you write it there, that thing stays with you. Okay, so whenever you are practicing, it is very important that not only listening to something, you also, if you write down the same things, it helps you to improve your memory. Basically, the things that you cannot remember, you have to write it down so that you can slowly improving on that. That is again second law of thermodynamics, right? Now let's see one more important application of second law, which is Carnot cycle. Carnot cycle, Carnot engine. Carnot cycle is an ideal version of engine. Even ideal engines, they do not have 100% efficiency. That means it cannot convert entire heat into work. Why? Because Kelvin, there is a old grand uncle Kelvin, he said that whatever heat you absorb, you cannot take the entire heat with you. Some of the heat you have to give it back. So this is an example of Carnot cycle. So basically Carnot cycle is basically using ideal gas. It is using ideal gas as its working substance. In our case, we do not use ideal gas. We use petroleum and air mixture in our engines. That's why our engine is not as efficient as Carnot cycle. Now you cannot use ideal gas. Ideal gas will not produce any heat on its own. Okay, so what is the processes involved? So first process is isothermal process. So that means here temperature is constant. Isothermal process. Here what happens? Isothermal compression. You are compressing the gas. So basically in engine what happens? You first compress the gas, okay, then you burn it, then it expands, and then again you change the you release it in the atmosphere. So basically that's how an engine works. So here if you see that the first pressure and volume, pressure is increasing, not pressure increasing, but anyway the volume is increasing. So it is isothermal expansion. So you are basically opening the valve so that gas can go into the engine. So here basically what happens is isothermal expansion. Isothermal expansion. Okay, now what you are suddenly you are changing the pressure, you are decreasing the pressure. Okay, as you can see, pressure from P2 suddenly falls to P3, and this is an adiabatic process. Again it is expansion, it is adiabatic expansion. Okay, any Carnot cycle is basically consisting of 4 stages. First stage is isothermal expansion, then adiabatic expansion, then you start compressing the gas. You start compressing the gas. Now here again the temperature is constant, so it is an isothermal process. So isothermal compression. Okay, now isothermal compression happens here. The gas is slowly compressed, then you again allowed the compression to happen suddenly. That is adiabatic process. Again it is adiabatic compression, and this is a cycle, it continues to happen. So and that's how our engine that is being working inside any vehicle, if you observe watch a video of any working engine, they all work on this basic principle. Now in our case, isothermal process is not completely possible. Most of our process is adiabatic. Why? Because isothermal process is a very slow process. You are keeping the temperature constant. Okay, so isothermal process is very difficult to achieve, but we can achieve the adiabatic expansion, adiabatic compression. Adiabatic process is much easier to do in our real life. Okay, but isothermal process is not. So this is how Carnot engine work. And remember that in Carnot engine, the efficiency depends on 2 things: the temperature, the initial and final temperature. These 2 temperatures are very important for Carnot cycle processing. Okay, so Carnot cycle is basically the efficiency is 1 minus T2 by T1, or sometimes 1 by Q2 by Q1. So Q2 is the heat that is being absorbed during the first process and the heat that is being released in the second process. So this is the process on which the efficiency depends. Obviously efficiency of none of the even ideal system is not 100%. This is ideal system. And also you remember that T2 by T1 is Q2 by Q1 for any Carnot engine process. Okay, now let's solve one question. Carnot engine takes 300 calories of heat from a source at 500 K and rejects 150 calories of heat to the sink. The temperature of the sink is, so the formula that I told you, exactly the same thing. So it is basically takes 500 calories heat and its temperature is already given in Kelvin. Remember, this temperature has to be in Kelvin. Okay, many cases they will give the temperature in Celsius. You have to convert back into Kelvin. Remember, don't forget that. Okay, they will say the temperature of the object is 100 degrees Celsius and the sink is 0 degrees Celsius. What is the efficiency? Do not do divided by 100 and 0, you get infinite efficiency. That is not possible. You have to do it, you have to convert it into Kelvin, then only you will get the answer. Q2 is also given in this problem, 150 calories, and they ask you what is T2. Okay, so you know that T2 by T1 equals to Q2 by Q1. So T2 is actually Q2 by Q1 into T1. So what is T2? Q2 is 500 Kelvin. Sorry, Q2 is not 500 Kelvin. Q2 is 150 Kelvin. Q1 is 500 Kelvin, and T1 is 500. Sorry, again my mistake. It is not 500. 500 is the temperature. So 150 calorie by 300 calories. So it will cancel anyway. So unit does not matter, into 500. But temperature has to be in Kelvin. Remember, the temperature has to be in Kelvin. So you get 1, you get 2, so you get 250 Kelvin. So the final temperature is 250 Kelvin. So the temperature of the sink is 250 Kelvin. Okay, so remember this. It's very important to remember kinetic theory of gases. So so pressure of an ideal gas. So what is the meaning of pressure? Pressure, obviously, when we keep a gas in a container, what happens is that the gas exerts pressure. Okay, so that pressure is basically measured using this formula. So here you can measure the pressure of a gas. M is the mass of the gas, N is the total number of molecules, V square bar is actually average velocity. Okay, square of the average velocity. Okay, so average kinetic energy of the gas molecule is half mv square, right? If we know the velocity, if we know the mass, we can calculate the kinetic energy. That kinetic energy turns out to be half mv square, and that can be related to the pressure as 2 by 3 n into E, because here we have 1/3, here we have half, so that can be adjusted like this. And this is this proves that the pressure of an ideal gas is proportional to the mean kinetic energy. Remember this. Here E always represents, in case of gas, is mean kinetic energy. Okay, here E is also mean energy. Now RMS speed of gas, this is very important concept. RMS speed of gas and as well as RMS speed of sound speed of sound in gas molecule are related to each other. So RMS speed of gas can be written as 3RT by M. Okay, you can calculate from there square root. This is the root square mean. Now if you take the square root of that, you will get the VRMS, which can be proven. That proof is obviously not going to come in your KCET exam. Square root of 3RT by M. R is the ideal gas constant, which is equals to 8.03 approximately. Okay, and M is the molar mass. Okay, so from there you can also convert it into 3 kBT by M. If you put I think this is a mass of one molecule. There is a small mistake. This is mass of one molecule. Here is mass of the all molecule. If you multiply n with this, you will get this answer. Okay, I need to check that once. Anyway, let's move on to the next concept, equipartition of energy. So this is the one of the most important concept from this chapter, and based on this concept we have seen a lot of questions came in the past. Okay, so only one concept, one page of this chapter. If you are not studying the chapter completely, at least study this. This is very, very important. In equilibrium, total energy is equally distributed in all possible degrees of freedom, with each mode having an average energy equals to half kBT. Now first I will explain the term degrees of freedom. What is the meaning of degrees of freedom? Degrees of freedom means how many direction a gas molecule or a particle, a molecule, not only a gas molecule, any molecule can move when they are free. Okay, for example, I can move in the forward direction, I can move in the backward direction. Okay, I can move in this direction as well. I can jump up and down as well. Okay, gas molecules also can move like that. If there is only one molecule, it can move along x-axis, along y-axis, and along z-axis. Okay, it can move along x, y, z, three direction. Okay, so x, y, z are considered to be three direction. Okay, so this is the three direction. That means the degrees of freedom of a monoatomic molecule is 3. Okay, now what about a diatomic molecule? Diatomic molecule means it has two molecules connected by one single string. Okay, they are joined by a string or a molecular bond. Okay, now what will happen in this case? How to calculate? Now in general, you can say that okay, this combination can again move in the three direction x, y, z, and then they can rotate. I will tell you an easier method to find that. So here we have, if we consider only one molecule, remember one molecule always have 3 degrees of freedom, no matter what, right? Here we have another molecule, it will also have 3 degrees of freedom, but here they are joined by one bond. That means the degree of freedom for a two molecule will be 3 plus 3 minus 1, that is 6 minus 1, that is 5. Okay, this is how you can remember for triatomic molecule. Now triatomic molecule, if they are in a straight line, order, okay, for example carbon dioxide. Okay, carbon dioxide is like this, right? Now here we do not consider double bond, only one bond is considered. So double bond is actually considered to be one single chain. You can consider the chain or linkage. Okay, here they are actually linked in a linear fashion. So if they are linear, then their degrees of freedom is actually 5. Okay, you do not need to consider the third molecule. But if they are non-linear, they are at some angle, for example water, okay, H2O is oxygen here, hydrogen here, hydrogen here. So what is the degrees of freedom? Again 3 for this, 3 for this, 3 for this, and how many bonds are there? One bond here, one bond over here. So it will be 3 plus 3 plus 3, that is 9 minus 2. Okay, so the degree of freedom for a triatomic molecule will be 7. Okay, in general, more than 3 atoms can always be somehow configured into this, and generally they have 7 degrees of freedom, except there are few special cases. Otherwise generally they are, for example CH4, they have a tetragonal structure, so that can be different from this. Now one more important thing is that in case of solids, apart from linear degrees of freedom, these are all called linear degrees of freedom. Linear degrees of freedom, DOF. DOF is degrees of freedom. In case of solid, apart from linear degrees of freedom, we also have something called vibrational degrees of freedom. Okay, vibrational degrees of freedom are considered generally 3. For solids, the degrees of freedom is extra 3 you have to add. Okay, and generally solids are monoatomic. Most of the solids are monoatomic, even they form crystal structures. Most cases they are monoatomic, and we consider that it has a 3 degrees of freedom due to linear degrees of freedom, and 3 vibrational degrees of freedom. So total degree of freedom for a solid molecule is 3. Okay, they can not only move inside the substance, not by much, but even again it can move. Also it can vibrate. Okay, because of that vibration, it will have a extra 3 degrees of freedom. So these are the important things. Solids have how many degrees of freedom? Solids have 3 plus 3. This is linear, this is vibrational. Remember this is a small nugget. Now what? Now let's move on to the formula that we are discussing, that equipartition of energy. Equipartition energy can be applied to solids as well, not only gases. It says that in equilibrium, energy is equally distributed across all degrees of freedom equally, and that is half kBt. So suppose the degree of freedom is 3, then what is the total energy? Total energy will be 3 by 2 kBt. Okay, the mean energy, the total mean energy is 3 by 2 kBt. Ideal gases are monoatomic always. Ideal gases are always considered monoatomic. Okay, they do not form any bond between them. They are spherical, rigid. Okay, they collide with each other elastically, if you remember the postulates. So for ideal gas, they are monoatomic and their mean energy is 3 by 2 kBt. For 1 degree of freedom, half kBt. For 3 degrees of freedom, 3 by 2 kBt. Okay, if you go for diatomic gas, it will be 5 by 2 kBt. Why 5 by 2? Because degrees of freedom is 5. For polyatomic gas, it will be 7 by 2 kBt. Okay, for solid, it will be 6 by 2 kBt. Okay, now total internal energy. So total internal is, this is the mean energy. Mean energy means the kinetic energy that is with it is moving. Now if you want to calculate the total internal energy, now what is the meaning of internal energy for gas? Internal energy for gas is basically its kinetic energy. Okay, so basically the gas molecules or gas particles are moving faster. Okay, and that's why its energy is increasing. So whenever you supply energy to a gas, the molecules of the gas starts to move faster, and that's why it consumes some part of the energy. If you remember first law of motion, in first law of motion we said that gas molecules are taking energy and remaining energy it is giving back to work, right? So the energy that is actually it is consuming, that energy goes into the kinetic energy of the gas molecules. So basically that increases its kinetic energy and gas molecules moves faster. So from this energy formula we can actually calculate the total internal energy of the gas. Total internal, not the internal energy difference. Total internal energy will be 3 by 2 kBt, that is for energy per molecule. And if you multiply, if you take 1 mole of gas, obviously for 1 mole of gas, if you multiply it with the Avogadro number Na, you will get, now Kb into Na is actually R. Kb into Na is actually R. So this will be RT. So 3 by 2 RT. Okay, in the formula I think the mistake I made here, it is correct. Here it will be small m. This will be small m. Okay, small m is the mass of one molecule, which is total mass divided by Na. So this confusion is also clear. Okay, so that's why it is small m here. Okay, now next is now what? So total internal energy is 3 by 2 RT. Now 3 by 2 RT, 3 by 2 R is actually CV. CV can be calculated as 3 by 2 into R. Okay, again derivation is not important. CV can be written as 3 by 2 R, and change in internal energy, change in, very important, change in internal energy can be written as CV delta T. Change in internal energy dependent on the change in temperature. So if you change temperature, then only internal energy changes. So if you remember in the thermodynamics chapter, I told you that internal energy dependent only on change in temperature. So change in temperature happens, internal energy changes. So that means it will be CV delta T. Now consequently the work done by the gas can be calculated as Cp delta T. Based on these two formulas, we have seen some question, so that's why I am including these concepts in this lecture. Okay, delta U is equal to CV delta T and delta W is equal to CP delta T. Okay, now molar specific heat of solids, as I mentioned, for solid also this law is valid, and if you calculate, the molar specific heat of solid can be calculated as 3RT. Okay, because for solid the degrees of freedom is 6. So if you put 6 by 2, it will be 3, and you can calculate molar specific heat for solid. Now solid do not have separate specific heat for volume constant and pressure constant. That's why it is general molar specific heat. It is given by 3RT. Okay, remember this. Now next is ratio of specific heats and degrees of freedom. So CP's general formula is F plus 2 by 2. Okay, for ideal gas F is 3, but for any other gas, if it is a diatomic gas, triatomic gas, you have to put the corresponding degree of freedom here. Generally, our most 99.9% times for KCET, the value you need to remember is this is optional. Okay, you generally I have not seen any question for polyatomic gas, but for monoatomic and diatomic, the values are 1.67 and 1.4 are the values. Okay. So degrees of freedom is sorry, I just got little ahead. So basically what I am trying to say that the ratio of specific heat is Cp by Cv. Okay, gamma PV to the power gamma equals to constant for adiabatic process. If you remember, this formula we have used. So PV to the power gamma equals to constant for adiabatic process. So similarly here, what is this gamma? Gamma is Cp by Cv, ratio of the specific heats, and in terms of degrees of freedom it can be written as F plus 2 by F, and you can calculate gamma for monoatomic, diatomic or polyatomic, and most cases it will be, you just need to remember the gamma value for monoatomic and diatomic. If you forget, if you remember the formula, you can put for monoatomic F is 3, for diatomic F is 5. Okay, and if you put that, you will get this result. Okay, so this value is also important. And now mean free path is the average distance covered by a molecule between two successive collisions. We know that gas molecules are colliding continuously. They are moving in random direction and they are colliding with other gas particles, and in between two collisions it is traveling in a straight path, and that is called free path. And if you take the average of such free paths, you will get mean free path. So there is a molecule here, there is a molecule here, there is a molecule here. Suppose one molecule here, so this gas hits it, then travels in a straight line, then travels in a straight line. So suppose this is the path. Now if you add all these and then take the average, you will get the mean free path, which is denoted by this small l letter. And main thing that you need to remember is the mean free path is proportional to 1 upon n d square. Okay, what is n? N is the number density, okay, how closely the gas is packed inside the container, and d is the diameter of the molecules. D is the diameter of the molecules, not the container. It is the diameter of the molecules. So based on this might be one question you can expect, but I have not seen any question so far. So just if in case you get time, you should remember that mean free path is inversely proportional to number density and square of the diameter. Okay, now let's move on to a sample question. Using equipartition of energy, the specific heat in joule per kg per Kelvin of aluminium at room temperature can be estimated to be. Atomic weight of aluminium is 27. So here they ask you the using equipartition of energy, the specific heat of aluminium. So what is the specific heat of aluminium? We already know aluminium is a solid. So solid, for solid, what is the specific heat? It is simply 3RT, right? Now this is the molar specific heat. Now if you divide this by temperature, you get the specific heat. This is the specific excuse me, this is the total specific heat. If you divide by temperature, you get the specific heat of solid, that is 3 into R, which is 3 into 8.03, which will come out around 25. Okay, here it's a 24.09. So it will be coming around 25. Now this unit is not in joules per kg per Kelvin. It is in joules per mole per Kelvin. Okay, this will be joules per mole per Kelvin. Now you have to convert this mole into kg. How to do that? So we know that the molar weight is 27. So molar weight is 27 and molar weight is represented in grams, right? So 27 grams. So 1 mole of aluminium is 27 grams. That is 27 into 10 to the power of minus 3 kilograms. Okay, so obviously to calculate the molar heat in kg, we have to divide this value by the 0.027 into 10 to the power of minus 3 joules per kg per Kelvin. Okay, that will be I think sorry, it will be 27. This is not, I have not converted it into kilogram, so it will be 27. So 25 by 27 into 10 to the power of minus 3, which will be very close to 1000. Again, we are not using any calculators. So 25 by 27, we are taking it as 1 into 10 to the power of plus 3, because this was in division, so this goes up, becomes plus, so it will be very close to 1000. Now if you see that only one result is close to 1000 is this one. Okay, obviously our result will be less than 1000. 25 by 27 will be close to 1000 but less than 1000. So less than 1000 but close to 1000 is only 925. So our answer will be 925. Very intelligent question.